pre-stressing of structures. There's many definitions, as I've found when I've been doing some research getting ready for this presentation. They're all there for you to read. The way I would think of it, or in terms of concrete, I would suggest the bottom one is a good one. So the pre-compression of concrete to counteract to a desired degree the tensile stresses that are expected to occur in service. So I'm thinking we've all probably done it in the past. You've gone to a row of books and you've picked them up by applying a force to the end. In simple terms, that is pre-stressing. You're applying a compressive load onto the structure, which is causing a friction interface between the books. The harder you push, the harder they push together. You can then lift it up in the air. I did mean to get some books out to demonstrate this, but I forgot clearly. Now, pre-stressing of structures, people often think it's fairly complex, but it has been around an awful long time. If we look at that boat at the bottom, that's an Egyptian boat, and they have, I'm not sure what the hull was made of, I'm guessing timber, but they used rope and twisted rope to cause a pre-tensioning effect in the structure. So that pulled the boat back up and gave it additional bending capacity. Another good example is an old type of saw, bowstring saw, I think this is called, where you've got the saw blade at the bottom here, pivot here and here, and the application of tension to the rope at the top here, or the string at the top here, causes the saw blades, the either end of the blade to be pulled out, which therefore puts the tension into the saw blade, which makes it better able to cut. Another good example of a membrane structure is an umbrella. When you push an umbrella out, you have the wire rods that push out, or the plastic rods that push out, that stretch the waterproof sheet into the right shape. That's another example of pre-stressing. Another early example is a timber wheel with an iron hub, or with an iron ring around the outside. So the timber wheel would be made up, the iron or the steel strap would be heated to expand it. It's then dropped over the timber, and as it cools down, it contracts and puts compression into the spokes. Again, pre-tensioning, or not pre-tension, pre-stressing of a structure. Similarly, something that all of us have probably ridden in our lives is bicycles. They are pre-stressed. Whether there's a couple of different arguments for how a wheel works, but the way I think it works is you've got a hub, or sorry, you've got the wheel itself, which is compressed by the action of the spokes being tensioned up, which puts that ring into compression. Generally, when we think of pre-stressing, we think post-tensioning or pre-tensioning of concrete. However, it's not the only material that can be pre-stressed. You can do it with steel, you can do it with cast iron, concrete, masonry, pretty much any material you can think of, people have done it. And when you start doing a bit of research, as I have been putting this together, you find more and more weird and wonderful ideas that people have come up with. So here we've got concrete lintels, which again, most of us are probably familiar with. They often are pre-stressed. So you can see the tendons there, the pre-stressed tendons. Here you've got a reactor vessel from a nuclear establishment where you have a cast iron vessel. And cast iron is very, very poor in tension, very, very good in compression. So they have taken those two things into account and made a pressure vessel that has a series of steel bands around it that keep it in compression, even though it's under high pressure. So you're getting the best of both worlds. Masonry, again, masonry can be pre-stressed. Foundation with your anchorage coming up here to the top of the wall, and then you can tighten up your anchorage, which puts a pre-stress into masonry wall, which gives it additional bending capacity. And there you can see one in practice. You can even pre-stress steel or pre-tension steel. Not very common, but it can be done. And again, it's normally done to increase the economy of a structure. Because we use higher grades of steel to form the pre-stressing component, it's lighter than the equivalent non-pre-stressed material, which gives us an advantage when it comes to weight and the economy of a structure. But that can often be offset by the complexities. So like everything, it's used in the right situation. So why do we pre-stress structures? It leads to more economical design. It's often lighter than the equivalent non-pre-stressed. Can produce a crackless structure. Now, what I mean by this is you can design a structure so it remains in compression throughout its entire loading cycle. That is a significant benefit with reinforced concrete construction because it's cracks that allow moisture and therefore allow rusting of reinforcing parts. Whereas if it's pre-stressed or post-tension or pre-tensioned, you can stop it cracking under all loading conditions and therefore improve the durability of the structure. So with a normal concrete beam here, figure 2, the application of a load causes the beam to bend down, which puts the bottom face into tension, top face into compression. The bottom face in tension, the tension is taken by the reinforcement, but you do get these microscopic cracks. And obviously if you apply more and more load, these cracks get bigger, which many of you may well have seen back in university days when you've undertaken tests on reinforced concrete beams. Now, if you do the same thing with a pre-stressed beam, you can apply a load to this tendon and anchor it off. So you're pushing on the end of the concrete. So as you apply the same load here, it bends, but because it's the concrete is in compression, you don't get cracking in the bottom face, and that improves the durability. Pre-stressed structures allow you to produce much longer spans than normally reinforced. When you come to long, large span structures, the dead weight is normally the driving load case. And if you can make the structure lighter by making it more economic by using pre-stressing, then you can end up with a bigger structure, a much longer span. They can deflect a lot less because of the application of the tendon and how it's designed. You can actually counteract deflection. We'll come on to that a bit later on. You can improve fatigue resistance, i.e. it's very good at taking repeat loadings because of this here, because you don't get this constant cracking. So if this was a bridge, for instance, the passage of a series of heavy vehicles might well cause these cracks to open up. And then it'll open and close, open, close, open, close, open, close. And over time, that can lead to fretting in the concrete. Whereas with a post or pre-stressed concrete, you can avoid that completely. The pre-stressing allows segmental construction, which again, I'll touch on a bit later. And you can have a significantly increased shear capacity with a pre-stressed structure, which can be beneficial in the right situation. So we're going to talk mostly about concrete today. Well, we are going to talk about concrete solely today. Now, there's two broadly different types of pre-stress. So that's pre or post-tension concrete. Simple terms, pre-stressed means, or pre-tension means stress applied to the steel tendons before the concrete is placed or before the concrete is hard. And post-tension means the stress is applied after the concrete has reached design strength. So on the left-hand side here, we have fairly typical bridge beams. These will be made in a precast facility somewhere. And the tendons you can see just poking through the ends here will have been pulled tight on a big form bed. Then the concrete will have been poured, placed, and then it's allowed to harden. And then you release the tension in the tendons, which is then locked into the concrete beam. With post-tension structures, you form your concrete structure with the tendons laid inside them. Once the concrete has reached design strength, you then apply a tension load onto these tendons and lock the stresses into the structure. So this one's pre, this one's post. That is the key difference. So as I mentioned there, this is how you'd go about doing it. So the pre-tension structure, you need to have a formwork in place, and you need to have some big, heavy anchor points either end of the item you're trying to cast. This is why this is generally done off-site. Or if you have a lot of similar beams, it might be worth setting up on site to do it yourself. Though generally today they're made in yards across the country and shipped where they're required. So the tendon is in and it's anchored, and then the tension is applied through jacking at the far end or one end. Then the concrete is placed. Once the concrete has reached design strength, you release the tension that's been applied either end, and it gets locked into the concrete. So as the tension is released in that strand, it has to transfer back into the concrete. Now, if you take something steel and you pull on it, you stretch it, which means that the cross-section area is reducing. As you release that, the steel will try to swell back to original size. That's what causes it to lock within the transmission zone. So for typical pre-cast, pre-tension concrete, they suggest the transmission zone is 40 to 60 lengths of the strand. And that's roughly where you'll get the maximum stress in the tendon. So all the concrete from here to the other end will be under compression. And from here to here, there'll be a gradual ramp up of the compression. As I said, it's generally off-site manufacture use it for. So buy some planks that pre-tensioned. Bridge beams that we use, standard bridge beams that we use throughout the country are generally pre-tensioned. You can see all the strands in the bottom there and a few up in the top here. U-shaped beams, all sorts of, there's a weird one or variety of pre-tension concrete available off the shelf pretty much. Now post-tensioned. Post-tension generally means in situ, excuse me, in situ on site. So you form your concrete, you place your tendons in the duct, but they're not tensioned at this point. You cast your concrete. Once the concrete has reached design strength, you anchor off one end and then apply a jack to the other end, or you might be jacking from both ends, depends on the length of the tendon. Once the jacking is complete, you can then lock the tendon off, and that keeps the tension force in the tendons, which is then in turn applied to the concrete and is pulling the concrete together. Typically, the tendon will run inside the concrete in a what's the one I'm looking for? In a sheathing, which is being cast into the concrete. So that provides a bond between the sheath and the concrete. Typically, you then grout the tendons in place. Excuse me. That locks the tendons into place and transfers the stress into the structure. Though the main transfer is carried out by the anchor plates either end. If this is grouted up and then you then cut through, you'll get an anchoring situation very much like this. So this is a little video here that actually probably shows it better than I just explained it. I'm going to jump through bits of it. So there's your normal reinforcement being placed, and then you put in the ducts. There you go. So there's one duct gone in. Not quite sure of the shape of that one. Two ducts gone in. Then pour your concrete and then wait for that to go off. And then this is the jacking. This will be the locking collar on one end. That's the jacking collar, sorry. So that jack is pulling on all of those tendons at the same time to put tension into them. And then it gets locked off. Cap them off. And then pump grout into them. Now the grout, the other function of the grout is it stops any long-term rusting or failure of the tendons, which can be quite a big problem with a post-tension construction. And then you can lift them into place, whatever your structure happens to be. So you don't necessarily have to do it in situ. You could do it on the ground and lift it up, which case study later on, they've done just that, which I'll go through. So if you're coming along to demolish a structure, how do you know if the structure is pre-stressed in any way? There are some giveaways. So segmental construction, so that's on large scale bridges here. Each of these is being precast and gets lifted up into place with a traveller and then is anchored to the next one with a tensioning system. So that's normally a giveaway. The structural form of a structure can often be a giveaway. If it's quite a long, slender structure, that often means there's pre-stress involved somewhere. Sometimes you get lucky and there's visible external tendons, or internal. So this is inside a bridge beam. Inside a structure very similar to this, and you can see the tendons run within the structure and are clearly visible. So if you get access to the void, you can actually see and find the tendons themselves, and you know with certainty that it is a pre-stressed or post-tension structure. Ideally, the asset owner has record drawings. That sometimes happens if you get lucky, but it's not always the case. Visible signs. So there might be anchorage points visible, or mortar infill or grout tubes that can indicate the structure. If you're really lucky, there might be a plaque somewhere that identifies the structure contains post-tensioning. There was a move for a period of time for asset owners to do this, to put a plaque up to make it clear that the structure contains post-tensioning, because there was a fear that people in the future demolishing them might not have access to record drawings, etc. Though how successful that actually was, I couldn't tell you. I've never, put it this way, I've never come across a structure that's had a plaque on it that told me the building, that the structure was post-tensioned. So if you look at your drawings and you see something that looks like this, you see these tendons here, that's a giveaway. That is a post-tension structure. Similarly, a cross section here, lots of dots here, that is a pre-stressed structure, typically speaking. There's a bit more to it than that, and there will also be other giveaways on the drawing. But if you get pretty manky copies of drawings, which is often the case, if you see tendon profiles like this, or you see pre-stressed or precast beams here, it's often a giveaway. If you open up, if you go to the site and you look on the ends of the beams, and there's what look like these mortar infill pockets, that's often a giveaway, because what happens is they put the anchorage points in here, and then to stop any corrosion in the long term, they've then filled it up with mortar or grout or whatever. And that can be a giveaway, and you can normally break that out carefully and expose the system and see for yourself whether it's post-tensioned, as this one here was. So this was an interesting building in London where the whole structure was done in precast concrete, and the spans were such that we thought they might well be pre-stressed, and a bit of investigation on site made it quite clear that they were, and that was the anchorage system that was found. But again, there's no other means of telling. There was no drawings for the site. There's no plaque anywhere telling you. It just came down to getting on site and having a look. So you've got a structure, you think it's post-tension, or you know it's or pre or post-tensioned, and you've got to demolish it. What are the hazards you've got to watch out for? A big hazard is accidentally damaging the tendons. So if you run a core through, diamond core, through a concrete bridge, you could very easily go straight through the tendons. You'd notice them, but no more than drilling through reinforcement typically. And obviously, if you take out a tendon, you've taken out the compressive force on the structure. If it's not grouted, you've got huge problems. If it's grouted, you've got less problems. But either way, it's not a good idea. If you damage the anchorages, so here, for instance, if you went at that anchorage point aggressively with a big breaker, you could well dislodge one of these collars and send that pinging around the site, which is a direct hazard to people. Stress reversal. So some structures, the post-tensioning effects or the tensioning effects are added in tandem with dead load being added to the structure. So for instance, if you had a big transfer deck above a railway line or above some other item, and you're building a 30-story building, as another story is added, it's not uncommon for another tendon to be tensioned up. So if you then start demolishing that building from the top to the bottom, you need to take that into account and release the compressive force that's been locked in through the tendons. Otherwise, you can break the back and reverse the stress in the beam itself. Quite a specialist area, not something to really just go into here, but it's something to think of nonetheless. It doesn't behave just the same as a reinforced concrete slab at all. If the tendons, so where are we going back to here? Yeah, so here. So the tendon is the steel anchorage, or is the steel wire that locks the force into the structure. If they aren't grouted in place, if you cut through them, that tensile force will release. That can lead to the tendons snaking out and the anchorage is releasing explosively either end of the structure. If it's grouted, It's unlikely to release explosively, but what you will find is that you've lost that pre-tensioning force across that section of the structure if you cut through them. Stress reversal due to change in support conditions. So if you've got a beam that's currently spanning, I don't know, say 30 meters end to end, sitting on bearings, and you pick it up with a spreader beam that's 10 meters long, you're going to get significant stress reversal due to the change in the support condition, which needs to be properly assessed. Condition of the structure. Post-tension structures are often being taken down because their life expired, and the condition needs to be taken into account carefully. So, for instance, one we're working at the moment, we know through monitoring that a lot of the individual strands that make up the tendons have been snapping due to corrosion because the ducts weren't grouted. The tendons are corroding, and then individual strands are releasing. So you've got to be very careful when you plan the demolition sequence and take that into account. Allow sufficient additional factors in the design that doesn't cause a problem. If you lose pre-stress across a cross section or through a cross section, that can significantly affect shear capacity. If only I could spell capacity, which in turn could lead to a shear failure of the structure. Shear failures have no warning and are sudden and catastrophic, generally speaking. So it's not something to be entered into lightly, that's for sure. This is just a little, after all these horror stories and warnings, just a little a mini case study of a bridge that we took out that was post-tensioned. I'll have to apologise for the watermarks. We did that because we included these images with a tender to show how we worked on post-tension structures before. So this is a RC post-tension structure. You see we lifted it out, pretty much maintaining the original support conditions, lowered it to the ground, and then buried at either end where the anchorages were, and then used a pulverizer to break out the concrete and release the stress in the tendons. So you can see it can be done safely. It just takes a little bit of thought. You can see there the actual ducts and the tendons themselves have been exposed, and it can be done safely in a controlled manner. And there they are. So that's the actual sheathing there that the ducts then run inside of. So that's the tendons themselves there and there. I've talked about grouted or non-grouted a couple of times now. So what that means is within the sheath, which is that there, are the tendons grouted in place. So you can see in this particular structure, the tendons aren't grouted. That means if you cut through here accidentally or on purpose for that matter, you will release the tension within those tendons, and that will cause the pre-stress to be lost within that section. So what do you need to see when working out how to demolish a pre-stressed structure? Ideally, you want the drawings. In an ideal world, you would have the drawings for the structure that would include everything to do with the post-tensioning or pre-stressing system that was used. And there's another spelling mistake. Often you will find that the design of the post-tensioning or system was left to specialists. So you might well have the drawings of the structure with the idealized tendon alignment, but the actual detailed design was done by somebody else, which can be a bit of a pain, but at least you've got a starting point. If the asset is owned by the Highways Agency or Network Rail, I believe they have a statutory duty to undertake investigations on post-tension structures on a regular basis. So they should be able to supply you with the post-tension special investigations, which should include, can include anything from a desktop study through to detailed investigation on site to open up and expose the ducts, the tendons, the anchorage points, everything to give you an understanding of the condition of the structure and how it's actually been built. Previous inspections and assessments of the structure. Again, anything that can help the engineer understand the structure and its condition is useful. Any constraints on how you're going to take it apart are also very useful. Now, generally speaking, in fact, most of the pre and post tension concrete structures we worked on, we've had drawings to some extent, though that's varied from 1 or 2 outline drawings through to full detailed drawings. Now, where the information is limited, there is a range of things that can be undertaken, from arranging investigations and actually going on site, opening up works and confirming the condition, the type of the system that was used, whether it was grouted or non-grouted, whether any of the tendons have failed or the strands of the tendons have failed, etc., etc. You can also look at doing stress testing of the structure, or putting strain gauges on the structure and applying a load to it to see how it behaves. There's any number of things that can be done to understand how the structure works, though the best one is knowing how it was built in the first place, ideally. Right, now we're going to go on to a few case studies of pre and post stressed concrete structures. So the first one is Regent Street in Leeds. This is, I should really remember what road this is, but I can't. Fairly central Leeds, dual carriageway over the top of the structure in each direction, passing over main road underneath. Now, this structure being taken apart in 2 phases to allow the new bridge to be built at the same time. The outer spans, so the pink and the green spans, are pre-stressed concrete beams, while the dark blue and the light blue here are post-tension beams. So this bridge had a bit of both. So side spans are pre-stressed and the inner spans post-tension, sitting on concrete abutments and concrete piers. Now, the central spans here had to be driven out on SPMTs due to constraints with methodology. The council would not allow percussive methods to be used to demolish the structure in situ because they are reusing the piers here and here in the next phase of the works when they rebuild the bridge. So, due to constraints with the site and where we had to take the bridge section to, we had to, we could only limit the size of the SPMT we could use. So Sarans did a swept path and worked out what SPMTs they could get away with and the rest of it to make the scheme work. Now, that meant that we couldn't pick the bridge up in the to match the existing conditions. So ideally, we would have supported the bridge here and here to match the existing load path and existing condition for the structure. That wasn't possible, which meant we had a beam. I think the longest one's about 30 meters and we had to pick it up at 18 meters centers. You can see straight away that that's reversing the stress that's currently within the structure. And doing so meant we had to think carefully about stress history with the structure and how it was built, and therefore how it would behave when we took it apart in this manner. So if you look at the moment in the original condition, sorry, it's 34 meters is the worst one. Excuse me. The moment in the original condition is that the red line there, and when we picked it up at 18 meter supports, it's the blue line there. So you can see we are reversing the stresses within the beam, which therefore meant the tendons are actually trying to break the back of the beam when we pick it up. So to justify how this worked, we had to understand how the structure was built. Now these beams were lifted up individually, so they were cast. I'm not sure if they were cast on site. I would think so. Then they were post-tensioned. Then they were lifted up onto the bridge bearings into place here. At which point the decks were cast. The in-situ decks were cast here. So that means when those beams were sitting, spanning from pier to pier, they had to support the dead weight of the wet concrete. Now that's important because that means that with the just dead load on this structure, this top slab is not carrying, is not in bending, i.e. it's only spanning from beam to beam. It's not involved in carrying the moment due to the dead load of the structure. That means that once we reverse the stress, we can use the tensile or the tensile stress available in the slab and in the steel in the top of this beam to counteract the reversing stress. And the analysis demonstrated that this worked and that we could remove the bridge as we did. This was all Cat 3 checked and passed off by the council. And there it is on the back of the SPMT, the first section being rolled out. And that's when you really see the scale of what you're doing with the size of that cantilever sticking out there. Makes some quite good pictures. You can see it's been jacked down, that one as well, hasn't it? Yeah.
Yeah, Angus, just to give credit, the pictures from Leeds Council.
Okay, that's it, from Leeds Council. Well done, Chris.
And Jordan said the roads with the A64M over the top and the A61 below.
So A64M over the top, and what was it below?
A61 below.
A61 below, there you go. Glad Jordan was there to help us out with that one. He should know, he was on site doing it. So there you can see Saren's kit in action again, and this is a jacking system here. So once the bridge had been brought out, you can actually jack it lower to then transport it down, which increases the stability when it's being moved. The pre-stressed beams on the outside, so the outer spans, were fairly simple compared to the post-tension ones, because we maintained pretty much the same point of support as they are currently. So that the bending hasn't changed significantly on the pre-stressed beams, and therefore we could justify it quite simply. We did take into account the additional compression due to the slinging arrangement, but and there it is in action. Again, a nice big Saren's blue crane there. Churchill Way, I'm not going to spend too much time on this one because I've done it enough times now, and there's a webinar available, an hour and a half of me, Jordan, and Tom wittering on about it. So if you want to go and look at that again, you can.
I'll put the link in the chat.
Okay. So this was a pair of 230-metre long post-tension viaducts in Liverpool city centre. They were continuous. Continuous post-tension structures are even more of a pain in the backside to analyse, because you get parasitic or secondary moments due to the post-tension effects. Again, I'm not going to go into detail on that here. Suffice to say, it gives you a bit of a headache. Now, these ones on this structure, the tendons were all fully grouted. We sliced it into sections and we lifted it down with, or moved it out with Saren's SPMTs again. This was a Sam Evans job. Saren's doing the SPMTs again. This is fairly typical of a post-tension structure. You look at this and you think, yeah, that's probably post-tensioned. Voids within it as well. Fairly thin webs relative to the size of the structure. And as we slice through here with a wire saw, this is the face of one of the tendons. You can actually see here where we've cut through. You can see that the steel tendon has retracted slightly, just a little bit, but that's to be expected because it then has to re-anchor. And it's that same effect I was talking about earlier. If you stretch a piece of steel, its cross-sectional area reduces because it's got longer. And then as you release that tension, it swells or it gets big again. It's Young's modulus. That's what dictates that behavior, stress-strain relationship. It then expands and locks itself back into the grout matrix again, which allows it to re-anchor. So that section has still got the post-tension effects in place. It's just another close-up of one being cut through. And another one there. You can see that one. That one's retracted slightly. Those ones haven't retracted at all, really. Whereas if they had been non-grouted, you can imagine that those tendons would have just disappeared into that void and you'd have lost any post-tension effect on that structure whatsoever. Though in this case, we'd analysed it, improved, it would still work, but that's what would have happened. And you can see, because it was grouted, it could then be sliced up into pieces and then taken away and processed off-site as you would with any other structure. So why it's something to be respected is not necessarily something to be feared dealing with post-tension structures. You need to make sure you get the right advice at the right time. Another one, Old Slade Lane. A bit of an unusual bridge, this one. A lot of post-tensioning going on with this structure. So the main deck is post-tensioned across here. It also had post-tension backspan and support, and the piece that goes under the road and connects the two foundations together was also post-tension. So it had a right mixture of bits and pieces of this job. If you look at the section through the bridge, it looks something like this. So that's a section through probably around here, and the post-tensioning ran through the web here and the web here. This had a mixture of in situ post-tension with precast components as well. It was a very, very unusual structure. There's a few of them on the M4. So simple terms, we took off the cantilever sections here, which were the footways, and then we broke out the top and the bottom of the deck. So we broke out this and this. So you're just left with the post-tension beam spanning across with a couple of locations. We left the slabs in place to tie it all together. Put containers down on the deck because as we get to this stage here and you break through, this was going to rotate around the foundation and drop onto the deck at some point as you broke across here. So we then broke out the back spans that released these, which were pre-tensioned, post-tensioned as well. That's the end of that one. There is a video of it online, but I couldn't for the life of me find it. Jordan will probably now pop up with it and say, here's the video. Again, understanding how the structure worked and then coming up with the demolition sequence that could work with the system in place was all done with, I think that one had a full AIP submission as well, actually. Teapot Lane was another, this one had a mixture of pre and post tensioning again. So the central span, the drop span here, sits onto these balance cantilevers. So this support here, and then the cantilever goes out, picks up the drop span. The back span comes back and was anchored down. So this had a post tension anchoring point here that held the back span down, same on the other side. This cantilever piece here, this was just normally reinforced, but it had a post-tension restraint at the end, and then the drop span was pre-tensioned, post-tensioned. So we lifted it out, maintaining the current load path, so keeping the supports very close to the ends of the slabs, as close as we could realistically. Drop them on the deck, place some rubble over either end of the, I think that's the next one, yeah, next one. Once that was lying on the ground, we then processed this, broke the slab, broke the bridge back to the support, or near enough to support, and then the back spans were lifted out. Now, they burnt through the anchoring point here, and lifted out the bridges, the back spans with the same crane. The reason that was done is because, again, we were keeping this pier and this pier here. The pre-tensioned, or sorry, post-tensioned drop span in the middle, put on the deck on road protection. We heat rubble up and a road plate over either end, just to stop any potential for the anchorages to release, because we didn't know if the tendons were grouted or non-grouted. So on the side of caution, protected the anchorage positions and breakthrough with that machine. That was all done quite happily. Hunterscombe was a bit of a beast of a job. This was CDC, this one. Post-tensioned longitudinal beams, but this structure also had transverse post-tensioning. So that means across the bridge here, so from side to side of the bridge rather than longitudinal, which is with the span. Now, this was quite common on structures back from 60s, 70s. They applied the transverse post-tensioning to tie the bridge deck together and get good load sharing through the structure. So this one, we had very, very good clear drawings, and it was fairly obvious that it was post-tensioned. in both directions. So this is a typical beam. You can see the tendon there and the tendon there. So they had one flat tendon and one curved tendon, or two curved and two flat tendons pretty much on all of them. You can see the anchorages at the end. So if you'd taken, lifted the beam out, you'd have been able to see the anchorages as they are here. And you can see the tendons in place there throughout the beam. In fact, there you go. I've done an enlargement already. Should have thought ahead, shouldn't I? So that's the anchorage at the end of each beam, and then a close-up of a tendon running through the structure. You can also see the lifting eyes here. So that again indicates that these were precast and then pre-tensioned and then lifted up onto the piers, and then the rest of the deck's installed from there. You can also see here they've got these holes that go through the beams, and they've got blocks for and like these holes were for an anchorage system, a post-tensioning system, a transverse post-tensioning system. Now, unfortunately, with this one, we had a post-tension special investigation, and it identified that all of the longitudinal and transverse tendons were grouted, apart from one transverse tendon. Unfortunately, they didn't know which tendon wasn't grouted. So that meant there was a residual hazard there. Now, given the fact that the anchorages were well above the height of the machines, and the machines were demolition spec, it was risk assessed and it was deemed acceptable to use demolition spec machines with an exclusion zone in place to allow the demolition to be completed. And nobody even spotted this non-grouted tendon during the works. So that one's completed successfully as well. That brings me to the end of 45 minutes of talking, and my throat knows about it. It's all right when you're doing these every week, but when you don't do them that often, your throat starts going. You want to know more? Temporary Works Forum, BS 5975 for Temporary Works. The book, The Temporary Works, Principles of Design and Construction. For the demolition side of things, you've got the NFDC, lots of useful stuff on there, and the Institute of Demolition Engineers, and also andon.co.uk for webinars and case studies on structures.